This is the delayed ACK. So this is the mechanism implemented at the TCP's receiver. Right? Now, in order to contrast TCP's receiver to go backend's receiver, let's bring back go backend receiver's finite state machine. And here it is, the go backend's receiver. There are only two events. First is getting a packet from the network layer, and it's not corrupted, and it's carrying the expected sequence number. Hey, this is the data packet we're expecting. So extract data out, pass it up to the application layer, generate the ACK packet, send back the ACK packet, and then increment the sequence number. So this is in fact the only significant event that we're expecting. All the rest, what the receiver of go backend does is just to send back the same ACK that has been generated previously. And back to TCP's receiver. So the first two events in TCP's receiver are these. Let's read through it a little bit. Arrival of in-order segment with the expected sequence number. Arrival of in-order segment with the expected sequence number. So both are events that's similar, right, to the significant event in go backend's receiver. Data arriving, not corrupted, and carrying the expected sequence number. So good news. We're supposed to generate ACK and send the ACK back. But at the TCP's receiver, okay, how we send the ACK back depends on the second condition here. Okay. So in event number 1, when all data up to the expected sequence number are already ACKed, okay, then we do one thing. If there's one other segment has ACK pending, meaning, hey, that segment there, we should be sending an ACK out, but it's actually pending. We haven't sent it out yet. Then we do this. Okay. Now, some of you might have guessed. Yes, TCP's receiver here is trying to do sending one ACK packet per 2 data packet received. So, if all data up to the expected sequence number have already ACKed, that's delay sending of this ACK. Okay. So let's wait for the next segment. When the next segment arrives, then we send the ACK. Otherwise, let's just wait for 500 milliseconds. When this 500 millisecond expires, yeah, we have no choice but to send the ACK for this data. So you see here, this is the other condition. When there is a back packet coming in and there is already one data packet that is supposed to be ACK, but the ACK is pending, which means it's waiting for the 500 millisecond. Then we immediately send one ACK, and this ACK here carries the sequence number of the later segment. Okay? And because the ACK is cumulative, so when that ACK comes back to the data center, it's going to clear both this packet and this packet. The third event is more like the default event. Okay, the similarity, however, is more, the action being taken. Okay, so when we receive a segment coming in that is out of order, meaning it's carrying a sequence number that's higher than the expected sequence number, then we will buffer the packet. So as a result, we detect the gap. So let me illustrate so that it's a bit more clear. Okay. Previously, we have received multiple packets, okay, and they are arriving in order. But suddenly, we get a packet that is out of order. It's not quite what we're expecting here next. So there's a gap in the sequence number of the packets received. In that case, upon receiving such out of order segment, upon detecting a gap like this, we send duplicate ACK, the old ACK that has been generated before. This ACK here is then carrying the sequence number of the latest packets received in order. The last event is this. Okay. Related to the gap we might see in TCP's receiver. So if a segment comes in that partially or completely fills a gap, then we generate a new ACK. The sequence number in the ACK here will be still the latest packet arrived in order. Okay, so this will acknowledge all the packets before that. Last is the fast retransmission mechanism. In order to explain why we need fast retransmission, let's go back a little bit. When we're describing when TCP sender experiences a timeout event, it's what? Dropping the window size down to 1 and setting the timeout interval to twice the current value. Okay. Because TCP sender, they're actually consider a timeout event being network being congested. Now this is very reasonable when there is a congestion. TCP sender here being a pipeline RDT sends often segments back to back into the network, hitting the congestion point. Router there, buffer full, no more space. All these packets arriving back to back gets dropped. Receiver won't be sending any ACKs coming back. Sender has nothing to do but to what? Take the timer that started when we send the train of packets out. And so eventually, timer expires, timeout event triggered, and therefore we slow down very drastically. Okay. So congestion, and we slow the sender down drastically, makes sense. But what if the packets go out did not hit congestion point? Okay. And we just have a random lost packet in the middle of it. What does the receiver do there? Yeah, it's going to get packet in order and then, a random loss. All the subsequent packet arriving out of order are going to generate duplicate ACKs coming back to the sender. If you recall TCP sender, when there are duplicate ACKs, what do? We ignore. So sender there will still take the timer and have a timeout event eventually. And we are still what? Reducing the window size to 1 and set the timeout interval to twice the current value. That's overdoing it, isn't it? And that's why we have the fast retransmission mechanism. Because if we see multiple duplicate ACKs, and when there is a hidden number of them, then you will probably guess there is a random drop right before the duplicate ACKs, okay? Or at the first unacked segment. So that is exactly what TCP fast retransmission is doing. When sender receives multiple ACKs for the same data, to be more precise, it's triple duplicate ACKs. Then we resend the unacked segment with the smallest sequence number because this is very likely the lost packet there. Okay. So then we don't have the timeout interval being long problem, right? Because we'll be waiting a long time to retransmit just this sporadic loss. Okay? And this is to exploit the characteristic of TCP being also pipeline. We send back-to-back segments. In case of sporadic loss, non-persistent loss, we could observe number of duplicate ACKs coming back to the sender and resend the packet real quick without waiting for too long. And this example illustrates triple duplicate ACKs. Host A here is the data sender, host B here is the receiver. So window size warrants that we send 5 packets in one train. Let's say packet number 2, sequence number 100 is lost. Then this is going to generate ACK for sequence number 100. But this one is lost, so it's not going to generate anything. All these subsequent packets, it's going to just, trigger the receiver to send the same ACK, back to back. So sender here receives the first ACK for 100. And this is the first duplicate ACK, second duplicate ACK, the third duplicate ACK. And this is when we begin retransmitting the first, the smallest sequence number that is unacked. And so TCP sender's pseudocode needs to be modified. And the only part needs to be modified is this event, when we receive an ACK packet from below. Okay. First of all, we extract the sequence number in the ACK packet. And this is the case when the ACK packet is new. And this is the other case when the ACK packet is not new. So in here you see we increment the count of duplicate ACKs. Okay. For each duplicate ACK, we increment this by 1. When the count for duplicate ACK is exactly 3, then we resend the segment. So this is fast retransmission of a lost packet. And then of course, drop the count back to 0. This is the last slide to summarize TCP's RDT. TCP's RDT is essentially go back in, so the base is go back in. But TCP being something that we actually need to implement and seeing running defines very clearly the equation to derive timeout interval. TCP is also a little bit more performance conscious, so timer will only get refreshed when there is a new ACK. When there is a duplicate ACK, timer does not get refreshed anymore, unlike in go back in. TCP there is also not only doing reliable data transfer, it also does congestion control, flow control, and everything else. Therefore, we see when there is a timeout, the retransmission window is only dropped to 1, and the timeout interval could be doubled. More unique in TCP are these. TCP receiver here is also trying to reduce the effort of sending ACKs. TCP receiver here also tries to buffer that arrives out of order. So memory is required as well as the TCP receiver, unlike the go back in receiver. TCP implements also fast retransmission, so for certain patterns of loss, we get to recover faster instead of waiting always for a timeout.